Welcome to my YouTube channel Cat, and today we will see in the magnetism section how the trajectory of a charged particle of charge Q will be there in a magnetic field B. Okay, so there in the magnetism section, okay, so we will see what is the trajectory of a charged particle in magnetic field B. Okay, so suppose that there is a magnetic field B which is everywhere. Okay, so suppose that there are some partitions like this. Okay, so firstly we will see without partition. Okay, or there is a magnetic field B which is everywhere. Okay, so suppose that this is a magnetic field B which is like this. This sign represents that magnetic field is inside the plane. Okay, so we will see different examples how the trajectory of a charged particle will be there. Okay, if it is sent with a velocity of v, velocity is v. Okay, so suppose that there was a charged particle which was sent from here with velocity of v and charge of q. Okay, so how will see the force? By the palm rule. Okay, so we will put this palm in the direction of this magnetic field. Magnetic field is inside, so inside, and this will be, these fingers will be in the direction of velocity. Okay, so these are in the direction of velocity and these are in the direction of velocity, and our palm is in the direction of magnetic field. So our thumb shows the direction of the force. It shows that direction of force is upside. Okay, so like this it will move. Okay, and it will come here. Okay, so like this the trajectory will be there like this, and it is a semicircle. Okay, like this semicircle will be there whose center is somewhere here. Okay, if the suppose that how we find that it is r is equal to mv by qb. Okay, r is equal to mv by qb, we know that, and we will find the radius from here. Okay, before telling the what is the trajectory, if the radius and the length here L, which is length of this compartment is L, if r is greater than mv by L, okay, so the particle will escape from here, escape. Okay, if the radius is less than L, okay, if radius is less than L, it will not escape and it will complete the circle here. Okay, so if we set here, it will just complete here circle. Okay, and it will not escape. Okay, so like this it will be there. If we will send from here, and the radius is greater than L, so it will escape, and if the radius is less than L, it will not escape. So before telling the trajectory, we should know that what is the length and what is the radius. We should always compare. If it is less than, then it can. If radius is less, then it will not escape. If radius is more, then it will only escape. And the trajectory is like this. So it is like this or this. We should tell by seeing the radius. Okay. So we will now see the next thing. Okay. So suppose that this is the same compartment. Okay, but the magnetic field is outside like this. So this dot symbol represents that the magnetic field is outside. Okay, suppose that this is the velocity of v and the charge is q. Okay, and it is sent. So how the direction of force will be here? Direction of force will be like this. You will tell. Okay, from the right hand, like this. So our thumb shows that the force will be downside. So this velocity is this. Like in the, or we can also predict by this. F is equal to q into v cross v. So velocity is in plus I. Okay. So and the magnetic field is in the plus k. So I cross k. So I j and k. So I cross k. So this is anti-clock. So I cross Okay, and we should always check what is the radius. R is equal to AB by QB. R is greater than L, then only it will escape, else it will be like this. Okay, it will not escape and come back. Okay, if the radius is greater than L, then only it will escape. Okay, because suppose that there is this circle, so we will always send from here or here. So like this half circle or so we can easily tell by checking this length and radius comparison. Okay, so suppose that there are more than one magnetic field. Okay, so what is the trajectory here? Okay, so suppose that there is more than one magnetic field, so like this. Okay, so where the magnetic field is inside, and here the magnetic field is outside. Okay, so what will be the trajectory? Okay, and here again the magnetic field is inside. Okay, so suppose that there is a charge when the magnitude is B, B and B. So magnitude is same. Magnitude of magnetic field are same. Okay, so suppose that there is a charge which is set like this. So we know that the charge velocity is V. So by the palm rule, it will show the direction of the forces upward. Or we can also tell by the F is equal to Q V cross V. V cross V. So V is in plus I and the V is in minus K. So I cross K is minus K, but one minus is also there. Force is in the plus J direction. So plus J, so like this. Okay. So again, if it will go here, so the velocity will be like this. Okay. So if the velocity is like this and the force here, the force will be here downside. Okay. Like this downside. Force will be this downside. So like this it will be there. Okay. And again the force will be upside, so again it will move up. So like this, then this, and then this, then this, and this whole curve will be differentiable. Differentiable means no corner will be there. Okay, so like this it will be there, and suppose that this is the velocity vector and the force will be like this. So the circle radius or the circle center will be in this only, like this here. So if we see the velocity vector is like this at an angle, so but the center will be perpendicular to this only. Okay, so like here only it will be there. So like this you can also see where is the center of this. Where is the center? Center is in this here, somewhere here. Okay, we can also see where is the center of the circle before telling the trajectory. We should also see what is the center and what is the direction of force. By this we can see what is the palm rule if we have to do early. Okay, or we have to save time. And what is the this curve nature of the curve is differentiable, or there will be no corner in the curves. Okay, and here it will be like this. The velocity vectors are like this. So when the velocity vector is like this at an angle, so how will it tell where is the center of the circle? The center of the circle will always lie at the 90 degree with the velocity vector angle. Okay, so velocity vector is this. So center will be in this only, like this only. So if we connect the center and the velocity vector, they will be at the 90 degree. Both the vectors will be 90 degree. If the point of the center and the point at which the particle is stand and the velocity vector, if we draw this vector and this vector, so both vectors will be at 90 degree. So it will help us to tell the trajectory. Okay, and how we will see this force vector by this force formula or by the rule we can also tell. Okay. So next thing is, when the velocity vector magnitude b, these are not same. One is b, one is 2b, one is 3. Then what we will do? Okay. So if the velocity vectors are not same, then if the this magnitude b is not same, then what we will do? So suppose that there is magnitude of b here, then 2b here, and then 3b here. So what will be the trajectory? We have to tell what is the trajectory. Okay. So suppose that there is a magnetic field here downside. Okay. And the here the direction of magnetic field is upside or the plus k direction. And here again the magnetic field which is 3d again inside the plane. Okay. So like this the vectors or the magnetic field magnitudes are given. Okay. So suppose that the velocity v of the particle is like this and the charge is q. Okay. So suppose that this trajectory is like this. Okay. So what is the trajectory? We have to tell when the magnitudes are different. Okay. So how we will tell? We will tell f is equal to qb cross b. So the force vector will be upside. So like this it will be their trajectory, and we have to always compare this length and radius. If the length is less than radius, then only it will escape. Okay, escape. Else it will not escape. Else it will not escape. Okay. So if it will be here. Okay, and when it will come here, the radius of this change r is equal to mv by qb. So the radius will be now less. R will be less than previous. So suppose that they all have a length of l. Okay, but the length of the radius will be changed. Length of the radius will be not less. So if the length of the radius which is now r by 2. So if the this b becomes 2b, so r becomes r by 2. So r by 2 is greater than l. Okay, then only it will escape. Else it will not escape. Okay, and here what it will become? R is equal to mv by qb. Okay, so r is equal to m. Okay, r is equal to mv by q into 3b. So r is equal to r by 3. Okay, so this is the concept. R is again equal to r by 3, and this again r by 3 is less than l. Then only it will escape. Else it will not escape and it will come back here. Okay. So if the r by 3 is less than l, then only it will escape. Okay. So here what will be the direction? Downside, and here again upside. Okay. So we have to always see that if the radius is always decreasing, r then r by 2 and then r by 3. Okay, so always the radius is decreasing, so we have to see from where it will escape and from where it will return back. Okay, so from where it will return back, at where the radius will be less than the length of this compartment of the length of this magnetic field where So if the radius and length values are given, we can easily tell when the n is this one. So the it will not escape. Okay. So suppose that r is 4 and the l is 2. So n will be